Hi, Assalamualaikum warahmatullahi wabarakatuh to our lecturer and my fellow friends. Today I want to present about performance of change memory using Paracache simulator. So I'm from section 4, computer architecture and organization. So firstly, I want to introduce you about our group name list. So first is Muhammad Aizzat bin Baharom. The metric card number is CE190134, and second is Muhammad Faris bin Muhammad Nahar, CE190084, and myself Muhammad Afiq bin Azmi, CE190151. So firstly, for the introduction, Paracache is a collection of efficient, simple, intuitive workbench for change mapping and virtual memory. Supported by detailed visualization of each step, Paracache will enhance the learning process by hand-on experience through step-by-step analysis. Users are encouraged to explore the workbench and observe different features of the component through the cycle of the workbench. So, in this project, we will use the Paracache simulation to test the performance of change memory. This simulation will test the hit and miss ratio of memory change using the direct memory and two-way assistive change in the Paracache simulation. The objective of this project is to measure the change performance, thus the memory size, change size, and given instruction to the change will be keep constant.
Assalamualaikum. My name is Mohamad Aizzat Baharom. My matrix number is CE190134. So today I'm going to demonstrate about direct map catch using Paracache simulator. So this is the interface of Paracache simulator. So first of all, we write the policies. We set into write back and write on allocate. The cache size is 16. So for memory size, we change it to 256. For offset bits is 2. So this is the instruction that we put, which we have 4, 5, 6, 7, 8, 9, 1F, 1D, and 1E. First value is going to be 3. First, we need to submit the right policies. When submit it, so submit the instruction for 3. And then the instruction has been converted from hex to binary. So when click next, the index requested will be searched in cache as highlighted in yellow. The index 0, 1, 2, 3. So binary number for 0 is 0, 0. Binary number for 1 is 0, 1. For 2 is 1, 0. And for 3 is 1, 1. So valid bit will be obtained and analyzed. This is the analysis diagram. The valid bit is 0. Therefore, cache miss is obtained. Cache is updated with a new data set. So this is the statistic for load 3, which we have missed for load 3. So the next number is 4. I submit it. The instruction will be converted from hex to binary through the instruction breakdown. So index requested will be searched in cache as highlighted in yellow. It will move to the cache table, and the value will be obtained and analyzed. So this is the analysis diagram. Value bit is 0. Therefore, cache miss is also will be obtained. Cache is updated with a new data set. Cache table is updated accordingly. Block 1 with offset 0 to 3 is transferred to cache. The cycle has been completed. So next for value 5, the instruction also will be converted from hex to binary through instruction breakdown. So in the index requested will be searched in cache as highlighted in yellow. So the valid bit also will be obtained and analyzed, and this is the analysis diagram. Since the valid bit is 1, the requested tag and cache tag is the same, so therefore the cache is hit. So the cache table is updated accordingly. Block 1 with offset 0 to 3 is transferred to cache. So the cycle has been complete. So the next for 6 is the instruction has been converted from hex to binary and allocated to tag. The index requested will be searched in cache as highlighted in yellow. So the valid bit will be obtained and will be analyzed. It will follow this is the analysis diagram. Since the valid bit is 1, the requested tag and cache tag is the same, so therefore the cache is hid. So the cache table will also be updated accordingly. Block 1 with offset 0 to 3 is transferred to cache. So next for value 7, the instruction has been converted from hex to binary. The valid bit will be obtained and analyzed. This is the diagram for analysis diagram when the valid bit is analyzed. So the valid bit is 1. It means that the requested tag and cache tag is the same. Therefore, the cache is hid. The cache table is updated accordingly. Block 1 with offset 0 to 3 is transferred to cache. So for value 8, the instruction also will be converted from hex to binary number. The index requested will be searched in cache as highlighted in yellow into the cache table for index number 2. The valid bit will be obtained and analyzed in the valid, and then the output is the analysis diagram. Since the value bit is 0, the cache is updated with the new data set, so the cache also is missed. For the cache table is updated accordingly. Block 2 with offset 0 to 3 is transferred to cache. For value 9, the instruction has been converted from hex to binary and allocated to tag. This is the analysis diagram. Since the value bit is 1, the requested tag and cache tag is the same, therefore the cache is hid. For value 1f, the instruction is converted from hex to binary. The index requested will be searched in cache as highlighted in yellow. This is the analysis diagram. Since the value bit is 0, the cache is missed, so the cache is updated with the new dataset. For value 1d, the instruction is converted from hex to binary. This is the analysis diagram. Since the value is 1, the requested tag and cache tag is the same. It makes the cache is hid. For last instruction is 1e. The instruction is converted from hex to binary. The index requested will be searched in cache. The valid bit will be obtained and analyzed. Since the valid bit is 1, the requested tag and cache tag is the same. It makes the cache is hid. So this is the final result of direct method cache, which we have hit rate 60%, miss rate 40%. So that's all from me. Thank you.
Hello, Assalamualaikum. Good day to you all. I am Faris bin Nahar, CE1900A4, and today I'm gonna present demonstration in two-way set associative cache. And first of all, this is our configuration, which the cache size is 16, memory size is 512, and the offset bits is 2, and we use 10 loads, which is 10 cycles for this process. And let's start. And click submit the configuration, submit the instruction. And the first one, the instruction is converted from hex to binary and allocated text, tag, index, and offset respectively, and in this ping box. And the index requested will be searched in cache as highlighted in yellow in this yellow box, and the yellow row over here. And the value will be obtained and analyzed. And this is our analyzed diagram. And most of the gate is missed, so the cache will miss. And the cache table is updated accordingly and complete. And we are already complete the first cycle, and moving on to the next cycle, which is load 4. Click next. All of the process will be repeating just the same. And this is our analysis diagram. By looking on the cache table, on the both of the cache table, the requested tag and the cache table the cache tag for first table is the same, and as you can see over on the analyze diagram over here, one of the gate is hit and another one is missed, so the cache will be hit. And moving on to the next cycle, which is load 4, click submit, and next. And this is our analysis diagram. And as you can see over here, both of the gate is missed, so the cache is missed, and the data will be updated accordingly. Moving on to the next cycle, which is load 5, submit, next, analysis diagram, and then look on the cache table and the analysis diagram. One of the gate is hit and another one is missed, so it will be hit. The cache will be hit, and the data will be obtained from the cache. Next, and moving on to the next load, which is load 6. The same process over here, generating the analysis diagram, and the requested tag and cache tag for first table is the same. And by looking on the gate, the first gate is hit and the second one is missed, so the cache is hit, and obtaining data from the cache. Next, and moving on to the load 7 for the next instruction, submit, next, analysis diagram, and requested tag and cache tag for first table is just the same, and one of the gate is hit and another one is missed, so the cache is hit, and obtain data from cache. Next, complete the load 7 cycle, and moving on to the next cycle, which is load 8, submit, next, analysis diagram, and the requested tag and cache tag is not the same at all. As you can see over here on the analysis diagram, both of the gate is missed, so the cache is missed. Obtaining data accordingly, and complete cycle. And moving on to the next cycle, which is load 9, click submit. Same process over here, analysis diagram, and requested tag and cache tag for second table is same, so the second gate is hit and the first one is missed. If one of the gate is hit and another one is missed, so of course it will hit, the cache hit, and the data is obtained from cache, and the cycle is complete. And moving on to the next load, which is load 1F for the next instruction, click submit, next, and this is our analysis diagram, and requested tag and cache tag is not the same at all, so the both of the gate will be missed, will be labeled as missed, and of course the cache missed. Moving on to the next load, updating data, and the next load is 1D. Next, analysis diagram. The requested tag and cache tag for second table is the same, so the second gate is hit and the first table is missed, so the first gate is will be missed. And if one of the gate is hit and another one is missed, and of course it will hit, the cache hit. Click next, data fetch from cache. Moving on to the last one, which is the load 1E for the last instruction, submit, next. This is our analysis diagram, and the requested tag and cache tag for second table is the same, so the resulting the gate will hit, and the first one of course is missed. One of the gate is hit and another one is missed, so of course it will hit, the cache hit, and obtain data from cache. And this is our statistic. we get 4 load missed, and the rest of it is hit. And this is our hit rate, which is 64%, and the miss rate is 36%. That's all from me. Thank you very much for watching.
So last but not least, the conclusion. Lastly, in this project, we gain a knowledge in theoretical and practical on how direct and two-way assistive change operate in the computer. Therefore, Paracache simulator played a vital role in order to achieve our goal, which was to observe how memory change work in practical way. All of the objectives are successfully gathered as we gain the expected result from the simulation. The work process was successfully done. So lastly, for the recommendation, the demand of current operating system put a strain on traditional technique to virtual memory address translation. The shift of 64-bit architectures as well as the demand to enable persistent and single address space system have increased the size and sparsity of virtual address space. So lastly, in the course computer architecture and engineering, the reconfigurable charge simulator was utilized. Overall, the course primary objective were met, as well as proving that the simulator is a compelling tool for introducing reconfigurable virtual system and chess design to reinforce student knowledge. So that's all from me. Thank you.